Hey, Professor. Can I ask you questions before we get started?
Sure. What's up? Hang on. Let
Yeah.
me let me lower the volume. You're kind of loud.
Oh, sorry. All right. Am I good now
Uh,
in terms of volume?
I'm trying. Okay, try again.
All right. Can you hear me?
Yeah. Okay. Go
Okay.
ahead.
So I just want to ask you. So for the project that we're doing, or
Yep.
the report, so we chose the topic of swimming. Do I have to do
Mhm.
basically every single thing that involves swimming, or can I choose like one subsection of something?
So my requirement is only five analyses in total. So how you choose to split up those five analyses is up to you. Uh,
Okay.
Now with swimming is a very dynamic activity. Uh,
Yeah.
I mean floating is probably wouldn't make for a good analysis. So uh,
Yeah.
I think probably the methods that we're covering now I think would be good. You can do a
Okay.
dynamic analysis, and maybe you do a dynamic analysis of let's take a certain stroke like a backstroke. Maybe you do
Yeah.
dynamic analysis of the arm during backstroke. Maybe you do a dynamic analysis of the legs. Those that could be two analyses, and then maybe you pick a different stroke. Maybe you do a dynamic analysis of the arm during breaststroke, and dynamic analysis of the
Okay.
leg breaststroke. So it's up to you in terms of
Okay.
how you.
So sorry, I didn't mean to interrupt. But
Mhm.
for the dynamic analysis, is that the stuff we're currently working on, or is that the stuff that we did several weeks ago?
So it's both, and so
Okay.
you can do a motion doing a motion capture study might be hard. You may be able to find some data on that online. I don't know if anyone has ever done a mocap underwater. Actually, that might be kind of interesting. But I think probably what's most likely is you're probably going to do what we're doing now, which is inverse dynamics.
Okay.
So you compute kind of the net forces that would occur at the joints, and then you'd probably obtain some motion capture data from some kind of paper elsewhere. So that's part of the report is to do some literature research, find some data, and then you can plug that data into the analysis that you're doing.
Okay, yeah, because I've been looking and I really haven't found any like motion capture stuff. So what I
Mhm.
was thinking of doing is basically have it like set up like the static, but then like the convert the force instead of just making it equal to zero, just make it so that it's like moving further, so there's an acceleration present. I don't know if that's something that would necessarily work.
That's essentially what we're doing in this section here. But in order to actually solve those equations, you do need kinematic information,
I
like
see. Okay.
positions and velocities and stuff like that. So in the absence of data, maybe you can model it, and so maybe you can give some simplifications in terms of like a backstroke's pretty simple. So backstroke, you can the arm is basically just like a windmill, and so you can maybe plug in some data from what you think would be for like the joint angles and joint velocities and joint accelerations during that motion. And then you can compute things like the forces on the muscles and joints that way. So
Okay.
yeah, so there's ways that you can in the absence of finding kind of hard data, you can kind of plug in approximations or assumptions to make the equations work.
Okay, but definitely try to look into motion capture for this, right?
Yeah, try to
Okay.
see what you. So there's I haven't looked into swimming before, but people have found some at least some motion cap, maybe not completely on the whole body, but maybe just for certain limbs or certain joints.
Okay.
People have found some stuff in the past on this on some of these things. So and if you're having trouble, I can help you look into it too and see what's out there and see what you can plug in for this analysis. Yeah.
Okay. What times are your office hours again?
My office hours are Monday, Wednesday after the lectures, so 5:30 to 6:30, and then
Okay.
Thursdays 1 to 2.
Okay. Because if I'm gonna over the weekend, I'm gonna just try to find a lot of this stuff, and if I have issues, I might just go to your office hours and try to see if
Okay.
you can help me figure it out.
Yeah, sounds good.
All right. Thank you.
Yep.
Yeah, so I just want to double check again. So I
Mhm.
just looked it up and I found something that does approximations, but not necessarily the exact. Would
Mhm.
approximations be all right, or does it need to be detailed info?
Yeah, yeah, approximations are fine.
Okay.
As long as you can reference it. And so, there's probably good reasons they did that approximation and with assumptions and stuff like that. So yeah, that's totally fine.
Okay, thank you.
Yep.
And then one last thing,
Mhm.
just to double check. And when
Yep.
you're talking about this motion capture stuff, this is essentially just the angle and distance for it, but I don't have to do that whole matrix stuff, right? I do the torque at or the moment at each joint and the reaction forces and all that, right?
Exactly. So if
Okay.
the approximation you found already gives you kind of the joint angles and the joint kinematics, then yeah, they've kind of already done the motion capture or they've approximated it in some way.
Okay, thank you.
Yep. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Hanging in there? Yeah, almost we got one more full week of class after this week and then Thanksgiving. Well, I guess technically we have the Monday of Thanksgiving week, but so I'll be here the Monday of Thanksgiving week, but obviously you guys don't have to be here. So because I have the lecture recordings and on Zoom and stuff like that. So but today we are going to be finishing up inverse dynamics. So this is the last topic that we're going to go over before the midterm exam. So did everyone get my email yesterday about the midterm exam? So midterm exam is going to be a week from today. Study guide is posted online, so definitely take a look at that. Um, and in terms of practice for the exam, I would definitely look at homeworks 4 and homework 5, in particular homework 5. So you can definitely expect a lot of, human motion capture, inverse dynamics to be well represented on the exam. Okay. Okay, so with that, the plan for today is, I think we last time, a week ago, we stopped right in the middle of an example. And so we're going to finish up that example today, just going over how to perform kind of this inverse dynamics analysis. And I have one more example to go over today as well. And so hopefully that will give you kind of a good overview of this method in terms of how to execute it. So you can, use it on the homework and do it on the exam as well. Okay. All right, other announcements I have is that a lot of groups have already contacted me in terms of setting up their groups for the final project. So thank you guys for doing that. So a lot of topics have been reserved already. So if you haven't had a chance yet to form a group, or if you need help finding a group, then make sure you reach out to me. I want to make sure that all the groups are formed before Thanksgiving, just so that you guys know who you're working with and what to research. I do have a couple groups that are just maybe two, maybe three people. So I may ask those groups to add additional people to your group. Especially for those who are having trouble finding a group. So don't keep an eye out for that. An email from me, and I may ask you to accept one other person into your group. Okay. If you are a person that hasn't found a group yet, and you're not really sure where to look, definitely let me know. I know who the groups are, so I can plug you in if I need to. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. Okay. So last Wednesday we started this topic called inverse dynamics. Okay. By the way, I apologize. I'm going to be sniffling a lot today. I hung out with my 10-year-old cousin over the weekend, and he kind of sneezed all over my face. So I'm a little bit under the weather. Okay, inverse dynamics. So what is the goal for inverse dynamics? Our objective when we do an inverse dynamics analysis is to take kinematics data, so basically data that you're going to obtain from like a human motion capture study, or another way to get kinematics data is that you may approximate it, right? Okay. And by kinematics data, what I mean by that is, information about the joint angles and joint angular velocities, angular accelerations. Okay. So those are the inputs of the model. So we need to input this kinematic data. And what we want to compute is we want to compute the net forces and net moments at the joints that are needed to cause this motion. Okay. So remember, that's the reason we call it inverse dynamics, because probably what you guys are used to in your previous courses in dynamics is that you're given the forces, you're given the moments on a particular dynamic system, and you use those quantities to compute the kinematic quantities. And so you use the forces, so you're able to measure any kind of external forces, external moments, external torques, and you use that to measure things like position, velocity, acceleration in a body over time. Okay. In inverse dynamics, we're given the reverse. So, we're given the kinematics data, and we want to find out, what forces or what moments are needed to cause this motion. Okay. All right. So just kind of keep that in mind. So, the goal of inverse dynamics is to compute forces and moments. And to kind of illustrate this, we're working on a particular example here. Okay. And so we're looking at the inverse dynamics analysis of a person doing a squat. Okay. And so it looks something like this. Okay. So of course, this is a very gross approximation of a person doing a squat, but we have our three joints here. So we have our ankle joint, we have our knee joint, and we have our hip joint. Okay. And what we were doing, basically our strategy here is to build a free body diagram of each segment of the person's body in this diagram. Okay. So that's going to include all of the forces acting on each of those body segments. So that includes, external forces, weight forces, things like that. Okay. And then through this free body diagram analysis, we're able to write out the equations of motion. Okay. And then from the equations of motion, we're going to be able to compute the net forces at each of the joints. And so we have 3 joints here. Okay. And so in total, we're going to have nine results here. Okay. Because at each joint, we're going to be able to compute the force in the y direction, force in the x direction, and a moment. Okay. So for the forces at the ankle, we have FAY, FAX, and MA. So that is the force in the y direction, force in the x direction, and the moment at the ankle joint. Okay. We have the same thing at the knee joint. We have FKY, FKX, and MK. Okay. And at the hip joint, we have FHX, ugh, my mind's all scrambled today. We have FHY, FHX, and MH. Okay. All right. So those are the 9 results that we want to get. Okay. And so the way that we were doing this is we were drawing free body diagrams of each body segment. Okay. So I believe where we left off last time was that we drew the free body diagram of the foot. Okay. And so that from that we were able to get expressions for FAY, FAX, and MA. Okay. So all 3 of these are done. And we are right in the middle of computing the same quantities for the lower leg. Okay. And so the next goal here is we're going to compute the forces at the knee joint. Okay, so that's FKX, FKY, and MK. So that's what we're going to start with today. Okay. All right, so that was just kind of a recap from last time. Any questions on this? Okay, all right, so let's get right back into it then. Let me go ahead and draw the free body diagram of the lower leg. Okay. All right, so our lower leg, it's angled like this. Okay. So the lower leg is the body segment that connects the ankle joint to the knee joint. Okay. Okay. So we have quite a few forces that are acting here. So first we have to define the gravity force. Okay. Right. So every body segment has a mass, it has a weight, and so we have to incorporate that into our free body diagram. Okay. And what we said was that this distance from the ankle joint up to the center of mass is R1, and the total length of the segment is L1. Okay. All right. Next, we have the net forces from the ankle joint. Okay, so we computed the ankle joint forces last time But the ankle joint forces are going to affect the foot and it's going to affect the lower leg. All right, and so in particular, we have F-A-Y, F-A-X, and M-A, okay? So these are the net forces at the ankle joint that we computed previously. Remember the convention that we have for these. So whenever you're inputting the joint forces onto a body segment and you use a certain sign convention in the last one, you want to make sure you use the opposite sign convention on this one. Okay. Okay. Because remember, every force has an equal and opposite reaction force that's applied on the reacting member. Okay. And so we want to make sure we apply that on in that one. Okay. So kind of the convention that I'm using here is that the first time that we see these net forces, I'm going to put them in the negative direction. And then the second time they appear, I put them in the positive direction, right? So if you look at all these ankle forces here, they're all in their canonically positive direction. So the Y force is in the up direction, the X force is is going to the right, and then the moment is going counterclockwise. Okay? Now for the knee joint, right? So we're going to have net forces at the knee joint as well. This is the first time that we're seeing the knee joint forces, in this problem here. And so I'm going to put those in the negative direction. So I have FKY going down, FKX going to the left, and then I have MK going clockwise. Okay. Okay. So again, this is the first time that we're seeing the knee joint forces, so I'm putting those in the negative direction. Again, that's just the convention that I use, but feel free to use something that kind of makes sense to you. But remember, whenever you're kind of switching from one segment to the next, you want to make sure that the sign is opposite of what it was from the last one. Okay. Any questions on this so far? Okay, good. All right, so let's go ahead and write out our equations of motion. Okay. So our equations of motion are nothing more than just the sum of the forces in the x direction, the y direction, and the moments. Okay. So I think we ended with this last time, but I want to make sure that because I think I kind of rushed it at the end, so I want to make sure I kind of explain this thoroughly. Okay. Okay, so for the x direction forces, this is pretty straightforward. So we only have two x direction forces. So we have FAX and FKX. Okay. So FAX is going in the positive direction. FKX is going in the negative direction. Okay, so we have an FAX minus FKX, and this is equal to mass times the acceleration in the x direction. Okay. So eventually we're going to plug in for that acceleration in the x direction in a second, but let's just write out all the equations first. Okay. Next, we have some of the forces in the y direction. So some of the forces in the y direction we have three forces. So we have FAY going positively upwards. Okay. Next force in the y directions, we have the force of gravity that's acting at the center of mass. So that's a minus m1g. And then we also have the y direction force acting at the knee. So that's FKY going in the negative direction as well. Okay. All right, and since we have this whole body's in motion, this is equal to mass times the acceleration in the y direction. And now the tricky part. So the sum of the moments. Remember, when we're doing a dynamic analysis like this, it really helps us to sum the moments around the center of mass. Okay. And remember, the reason we do that is that when we go to the right-hand side of this equation, okay, right, we want the right-hand side of this equation to be as simple as possible. So the simplest form of this equation is just setting this equal to the moment of inertia multiplied by alpha, alpha being the angular acceleration of this part, okay? There was another term there. Okay. And that other term there is kind of an adjustment term. If you were to sum the moments around, another point besides the center of mass, but that term involved a cross product. It involved a cross product of kind of a, like a vector that you have to kind of determine, cross product with the acceleration vector. It's just kind of a headache to compute. And so generally what I recommend for this one is to sum the moments around the center of mass. That way, you don't have to worry about that other term. Okay, so your right-hand side is kind of as simple as possible with just I times alpha. Okay. Now, unfortunately, that does mean that we have quite a few contributions to the moment equation, right? Basically, any force that's acting on a line that's not going, through the center of mass is going to contribute to the moment, as well as these point moments here. Okay, so MA and MK, right? But if you look at all the forces that we have in this free body diagram here, FAX, FAY, neither of those vectors are going to pass through the center of mass, right? So if you continue along with this vector like this, right, it's not going to pass through the center of mass. Same thing for FAX, okay? So FAX and FAY are going to contribute to the moment. Same thing for FKX, FKY as well. So neither of those pass through the center of mass, and so they all are going to have to contribute to the moment. Okay? So we have 6 contributions here. Okay, so let me go ahead with the point moments first. And so we have MA minus MK. Okay. So remember, point moments, we can just add them directly to the moment equation. Okay. Next, we have the moments that are contributed from the angle forces. Okay. So we have FAX right here, and it might help to kind of draw this angle here. Right. So the angle that the lower leg makes with the horizontal is θ1. So we know that information just based on our kinematic motion capture study. Okay. So we can compute the moment arm for this force here. Okay. So we have FAX, okay, multiplied by the vertical distance. So that's R1 times let's see, what did we say? All right, so I'm gonna go ahead and draw this triangle here. So that this triangle here has an angle of 180 minus θ1. Okay, just like that. Okay. And so if we look at this, the vertical distance there is sine of 180 minus θ1. Okay. Okay. And if we look at the direction here, that is going to go in the counterclockwise direction. So that's going to be a positive. Okay. All right, and then FAY, we want the horizontal distance. So we have FAY, R1 cosine 180 minus θ1. Okay. So we go back to this diagram here. We have FAY like that. And so the distance that we want is this one right here. Okay. Okay, so that horizontal distance there is R1 times cosine 180 minus θ1. Okay. And if we look at the direction of the moment, we can see that it is going counterclockwise as well. Okay, so that's going to be a positive. Okay. And then we have the contributions from FKX. Okay. So FKX, the distance between FKX and the center of mass here. Once again, I'm gonna go ahead and draw this triangle where this angle right here is 180 minus theta 1, okay? And so we have FKX multiplied by the distance, or the hypotenuse of this triangle is L1 minus R1. Okay. And then using trigonometry to get the vertical distance, that is multiplied by sine of 180 minus theta 1. Okay. And then once again, we're going to look at the sine here. And so if we trace out this FKX around the center of mass, we can see that it's going in the counterclockwise direction. So that's going to be a positive. Okay. Oh, question, yes.
Because we oriented them opposite, don't we already know that they're gonna go in theory the same direction?
Yeah. Yeah. So if you kind of are, and that's kind of the reason why I kind of do that convention there, is so that all these moments end up being the same sign. But since this is the first time, we're just kind of talking through it just to kind of see the logic there.
Except for the point moments then?
Exactly. Yeah, except for the point moments. Yep. So using that logic and knowing that all of these forces are going to contribute to the moment in the same direction, we know the last part here is going to be a positive. FKY L1 minus R1. Okay. And we're going to take a cosine of 180 minus theta 1. Okay. Okay. So that's our 3 equations of motion. So this is a lot more complicated than our equations of motion for the foot, just because we just have a lot more terms to account for here. Okay, but remember, F. Let me use green here. FAX, FAY. And MA, all of these are known from the previous step. And so, it's a little bit out of context today just because, we're kind of starting right in the middle of the example. But if you remember, we started the example last time and solved for those values. So these are already known. Okay. And so we only have technically 3 unknowns in this equation. So our 3 unknowns are FKX and FKY. Okay. And hopefully you can see from here that, FKX and FKY kind of appear by themselves in the force equations. And so you can use these equations to solve for FKX and FKY. Okay. And the last unknown here is MK, right? Which kind of appears technically on its own here in the last equation here. Now we have FKX, FKY here in the last moment equation, but if you plug in their values from the first 2 equations, then the only unknown in the last equation is just MK, okay? So there's quite a bit more algebra involved here. And so, because we have, more forces, our moment equations more complex, there's a lot more algebra to work through to solve for the unknowns, but, that's, this system is solvable. All right, any questions on this so far? Okay, good. But there is one order of business that we need to take care of before we move on to the thigh. Okay, and that is these quantities here. Okay, specifically AX and AY. Right. So AX and AY, if you recall from kind of your first physics course or dynamics course, this is the linear acceleration in the x direction and the y direction. Right. Now, what's the issue with that? Now, normally when you get kinematic data for a person in motion, you're not able to obtain the linear acceleration straight from the data, right? Remember, what does the data give us? The data gives us angular kinematics, so angular velocities, angular positions, angular accelerations, okay? And so these linear accelerations are usually not obtainable straight from the data. And so what we have to do is we actually have to derive expressions for these so that they're in terms of the angular kinematics. Okay. And so to do this, we need to make use of one of our best friends from calculus, which is the product rule. Okay. All right. So let's see how this is done. All right. So let's take let's take the x position of the center of mass. Okay. And let's use that to derive the x acceleration. Okay. And so if we look back up to this diagram here, okay. So the center of mass is this ball right here, right? So we want to get the x position of this. So one way that we can express it kind of very simply, knowing the fact that we have theta1, right? So remember, theta1 here is known. The other thing that's known is we know the distance along the lower leg between the ankle and the center of mass R1, okay? So a very simple expression for the x position of the center of mass, we'll call it x1, is just simply going to be R1 multiplied by cosine of theta1, okay? And the cosine term here actually accounts for the fact where, you know, if you look at that, if you look at the figure up there, you know, it looks like the whole lower leg is kind of bent, you know, backwards. And so theta1 here is actually going to be greater than 90. And so this accounts for negative positions as well. Okay. All right. So let's go ahead and take derivatives of this. Okay. So if we take dx1 dt, right? So we take the derivative with respect to time of the position. What we are going to get is velocity. Okay. So that's velocity in the x direction for segment 1. Okay. So we take derivatives of this. We have R1. R1 is just a constant. That's just the distance along the leg. And then we have the derivative of cosine theta1 here. Okay. Now you need to do a little bit of chain rule. So first thing you're going to multiply here is the derivative of cosine of x. Okay. And so that's going to be a minus sine of theta1. Okay. I forgot the R1 here. Let me put the R1 in there. Okay, so we have R1. R1 is just a constant that's just kind of along for the ride. Okay. But since, you know, theta1 here, theta1, remember, that's the joint, that's the ankle joint angle, right? Ankle joint angle. We know that, you know, since this entire body is in motion, theta1 here is also going to change with time. Okay. And so what happens when you take derivative of something that also changes with time? You have to use chain rule. Okay. So I guess, you know, not only do we need product rule, we need chain rule here as well, right? And so the derivative of theta1, so d theta1 dt, is nothing more than just the angular velocity of that joint, omega 1, okay? All right. And so from this, we get Vx1 is equal to minus R1 omega 1 sine of theta 1. Okay. All right. So we have that extra, omega term that comes out because of the chain rule. Okay. All right. So let's take another derivative. So let's take derivative of Vx1 with respect to t. So derivative of velocity is going to give us linear acceleration, ax. Okay. That's exactly what we want. So that's good. Okay. And so now we're going to take the derivative of this quantity right here. Okay. Now this is where product rule comes into play because we have derivative of R1. R1 is just constant, so that one is just along for the ride. And then omega 1 multiplied by sine of theta 1. So those are two quantities that both change with time that we need to take the derivative of with respect to t. Okay. Okay. So first thing, we're going to take the derivative of omega 1. So derivative of omega 1 is going to give us alpha 1. Okay. Alpha is just the angular acceleration multiplied by the second term, sine of theta 1. Okay, so remember, product rule is derivative of the first multiplied by the second plus derivative of the second multiplied by the first. Okay. All right, and then we have minus R1. Okay. We're going to take the derivative of the second term now. So that omega 1 is just going to come down. So the second term is derivative of sine theta 1. And so that's going to be, we're going to have another omega 1 that comes out due to the chain rule. And then cosine theta 1. Okay. Okay. And so if we simplify this, there's not that much to simplify. So we have ax is equal to minus R1 alpha 1 sine of theta 1 minus R1 omega 1 squared cosine theta 1. Okay. All right. Any questions on how we obtained that result there? Okay. So now that we have this expression for ax, we can go ahead and plug this back into our expression up here. Okay. So let me zoom out just so you can see it all. Because remember, when we did our equations of motion, we did it in terms of the linear accelerations. But now that we have an expression for the linear acceleration in the x direction, we can go ahead and plug that in up there. Okay. Okay, so let me go ahead and do the same thing for the y direction, but I'm going to do it fairly quickly because it's just kind of the same thing. Okay. Okay, so for the y direction, we need an expression for the y position of the center of mass. Okay. Okay. So that's going to be R1 sine of theta 1. Okay. And then just like we did with it for the x direction, we're going to take derivatives of this with respect to time twice. Okay. Okay, so we take the first derivative, we get Vy, comma 1, okay, is equal to R1 omega 1 cosine theta 1, okay. And then we take the derivative one more time with respect to t, we get R1 alpha 1 cosine theta 1 minus R1 omega 1 squared sine of theta 1. All right. And so with that, we're finally done with the lower leg. So after, I think maybe we spent maybe 20 minutes on it last lecture and, 35 minutes on it here, that's everything. Now, of course, these are very, very long mathematical expressions, right? right? These equations of motion were already pretty long, but then after you plug in for the linear accelerations, they become even longer, okay? But remember your goal. Remember the goal is to find expressions for fkx, fky, and mk, right? Now, I'm not going to go through all the algebra to find explicit expressions for these, and so it's mostly just kind of plugging in and solving it. So I'll go ahead and leave that to you guys. But at this point, you know, because we've written these expressions, we can kind of move forward under the assumption that we know all of the joint forces and joint moments at the knee joint. Okay? Okay. So we're going to go ahead and move on to the equations of motions for the thigh, but we're going to move forward with the understanding that we know fkx, fky, and mk. Okay. Okay. All right. So let's go ahead and move on to the thigh. Okay. And just like we did with the lower leg, we're going to start with the free body diagram. Okay. Okay. So for the thigh segment, it looks something like this. Okay. We have its center of mass. At the center of mass, we're going to assume that we have a gravitational force, m2g. Okay. We know the distance here. The distance from the knee up to the center of mass is r2, and the length of the entire segment is L2. Okay. We know this angle here. This angle here is theta 2. Okay. Let's go ahead and apply the joint forces that are coming from the knee. Okay. Remember, you know, we chose the knee forces to be going in the negative direction for the lower leg. And so we're going to put them in the opposite direction on the thigh. Okay. So we have F, K, Y. FKY, FKX, both going in their canonical positive direction, okay? And then MK going in the, whoops, wrong direction. Should be going the other direction. MK should be going in the counterclockwise direction, okay? And then we have the joint reaction forces at the, or the net joint forces at the hip, okay? So it's FHY, FHX, and then MH. Okay. Okay. So this actually looks very similar to before. Okay. So let's go ahead and write out all of the, you know, all of the equations here. Okay. So let's sum the forces in the x direction. That should be pretty straightforward. So we only have two forces in the x direction here. We have FKX going in the positive direction, and then FHX going in the negative direction. Okay. And that's equal to the mass times the linear acceleration in the x direction of the center of mass. Right? We'll compute that linear acceleration in a second. Okay. Then we have the sum of the forces in the y direction. And so in the y direction, we have FKY going up minus M2G minus FHY. Okay. And so that's equal to mass times the linear acceleration in the y direction. Okay. And then let's sum the moments around the center of mass, just like before, okay? Okay, so first we take the point moments, and so the point moments, we have a positive mk and a minus mh, okay? Then we have the moment contributions from each of the forces at the joints. Okay, so that's Fkx, Fky, Fhx, and Fhy. Okay. Okay, so first thing, let's do the forces at the knee. Okay. So that's let's see. So let's start with Fkx. So we have Fkx multiplied by R2, and we're granted a geometrical it's nicer here because the angle is acute. So, we don't have to do any kind of weird 180 minus an angle. So we have Fkx R2 multiplied by sine of theta 2. Okay. Let's look at the direction here. So Fkx, and so we trace that around our pivot point. You can see that's going in the counterclockwise direction. So that's going to be a positive. Okay. All right, and then we have Fky. So we have Fky multiplied by R2 cosine of theta 2. Okay. Very similar to our lower leg. But watch out for the direction here. And so if we trace out Fky, you can see that it's going around the pivot point in the clockwise direction. So that's actually going to be a negative there. Okay. Okay. So very important, depending on how you draw your figure, the signs of these moment contribution can be different, right? So make sure you kind of know. But the way that we do our sign conventions, we know that both the x forces are going to contribute to the moment in the same way, right? Because if you look at FHX, you can see that's going in the counterclockwise direction, and FHY is going in the clockwise direction. So again, we're going to have positive and negative for the other two. Okay, so if we have plus FHX, we multiply by the vertical distance between there. And so that's an L2 minus R2 multiplied by sine theta 2. And then we have the contribution from FHY. So we have a minus FHY multiplied by L2 minus R2 cosine theta 2. Okay. And this entire quantity here is equal to I times alpha. All right. Any questions on this part here? Okay. Good. All right, so just like we did with the lower leg, let's go ahead and compute the linear accelerations now. So AX and AY, okay? Okay. So to compute the linear accelerations, once again, we're going to start with the horizontal and vertical positions of each of the center of mass, okay? But we have to be careful here. So remember, when we're defining our positions here, right? Remember x2 here, this represents the x position of the center of mass of the thigh. Kind of what we've done so already, just by defining the position of the center of mass of the lower leg, is that we've kind of implicitly defined an origin for our domain, right? And so when we're defining the x position of different body segments, we need to make sure that we're consistent in terms of where our origin is. Okay. And so if you think back to, how we define the position of the lower leg, that was relative to the ankle joint. So that kind of implicitly, we were kind of assuming that the ankle joint was the origin of our system. All right. We need to be consistent here. So we need to keep the same origin. So this X position here of the thigh is going to be relative to the ankle joint, which is where our origin is. Okay. So we actually have two contributions to the X position here. And so we're going to have an L1 cosine theta 1. Okay. So this right there, that's the position of the knee joint. Okay. Okay. And then to that, we're going to add the relative position of the center of mass relative to the knee joint itself. So we're going to have a plus R2 cosine theta 2. Okay. Okay. So we have two terms here for the position of the center of mass of the thigh. Okay. Okay. So unfortunately, that does make our derivatives a little bit more complicated, but I want to make sure I kind of explain kind of how I got this thing here. Okay. All right. So let's go ahead and take derivatives now. So let's take the derivative of this expression with respect to time. So that's going to give us the velocity of the thigh center of mass. Okay. So if we do this derivative here, we get L1 minus L1 omega 1 cosine theta 1 minus R1, or excuse me, minus R2 omega 2 sine theta 2. I apologize. So this first term here is not cosine, but it's sine. Okay. Right. So the velocity is minus L1 omega 1 sine of theta 1 minus R2 omega 2 sine of theta 2. Okay. Let's take the derivative one more time. Okay. So taking the derivative of the linear velocity will give us linear acceleration. So we're going to have four terms here. We have minus L1 alpha 1 sine theta 1 minus L1 omega 1 squared cosine theta 1 minus R2 alpha 2 sine of theta 2 minus R2 omega 2 squared cosine theta 2. Okay. Okay. Any questions on how we got these results here? Okay, good. All right, so let's do the same thing for the y. Okay. The y2 here is going to be L1 sine of theta 1 plus R2 sine of theta 2. Okay. Vy2, so we take the derivative with respect to time, we get a positive L1 omega 1 cosine theta 1 plus R2 omega 2 cosine theta 2. Okay. we're going to take one more derivative of this expression. So get ay2 is equal to L1 alpha 1 cosine theta 1 minus L1 omega 1 squared sine of theta 1 plus R2 alpha 2 cosine theta 2 minus R2 omega 2 squared sine theta 2. All right. So again, these equations end up very, very long, right? And so there's just a lot of data and a lot of expressions that go into a dynamics analysis. Okay. So just like we did with the lower leg, what we would do is basically we would take this ay2 as well as this ax2. Okay. Okay. And so we take both of these expressions and plug them back into our equations of motion. And so even though these expressions here look quite intimidating, right? So our expressions for ax2, ay2 have a lot of terms here. But remember, all of these expressions here, they involve kinematic quantities, right? L1, R1, L2, R2, these are measurements that we know, okay? Theta 1, omega 1, alpha 1, theta 2, omega 2, alpha 2, all of these are known because we obtain them. These are all kinematic information, okay? And so in theory, everything that we've computed here, we should be able to plug in and find numbers for these, okay? Because ultimately the unknowns in this expression here are FHX, FHY, and MH, okay? So after we plug in for AX and AY, theoretically we have once again, we're gonna have three equations. They're quite extreme equations. There's a lot going on, but we have three equations that we can use to solve for these forces here. Okay. All right. And so that's the example there, okay? Now, normally what you would do at this point, if you did have your hands on that kinematic data, is that you would plug in that data into these expressions here. So you would plug in values for the angular position, angular velocities, angular accelerations for every single joint, okay? And usually those quantities are going to change with time, okay? And so for instance, you may, for this problem here, we had kind of, I guess, two main joints that we're looking at here that we have kinematics data for. So we have theta 1, omega 1, alpha 1, that's for the ankle joint, and theta 2, omega 2, alpha 2 for the knee joint, okay? Okay. So some typical data that you may obtain for something like this, we have theta 1, omega 1, alpha 1, okay? Theta 2, omega 2, alpha 2, okay? Usually in the most convenient format, this data here will be given to you in tabular form, okay? Where each row in this table represents those measurements at different points in time, Okay. Right. So remember, because at each time point, each of these kinematic data is going to be changing with time, right? Because the person's going through a motion. And so, for instance, theta one here, theta one is the joint angle of the ankle, right? And so that may go from, I don't know, 90 degrees when you're first starting up. Then when you start to bend down, maybe this goes to 80 degrees, 70 degrees, okay? And then omega one, maybe you start from a stationary position. So maybe your angular velocities and angular acceleration is 0 at first, but then as you start to bend down, these start to increase with time, okay? And so maybe the angular velocity here is minus 10 degrees per second, okay? Minus 10 degrees, or maybe we're accelerating here, okay? So the angular velocity is changing at a rate of 10 degrees per second in the first time step, and is changed by an amount of minus 15 degrees per second in the second time step, okay? Okay. And then the angular acceleration might be minus 10 degrees per second squared. And then in the second time point, you would plug in for that. Okay. And so basically, the way to use the inverse dynamics equation is that for each time point, right? And so for each row in the data table here, you'd plug in to your inverse dynamics equations. Okay. In particular, all of this kinematic information goes into the right-hand side of our, of our equations. Okay? You may have to plug in some angles on the left-hand side for geometrical purposes, but for the most part, most of the data is going to go into the right-hand side of those equations. Okay. Okay. And that's going to change with time. So, those equations here, those equations that we kind of spent, so long to derive, those equations tell you how the forces evolve with time, because the kinematic data also changes with time as well. So you will get for the joint forces. Okay. And if you have a reasonably kind of well-established or well-resolved motion capture data, this data table for the kinematic quantities is actually going to be very, very large. Okay. It's not uncommon to have thousands and thousands of data points, as you record the motion of someone going through a fairly long motion. Okay. And so because of that, it starts to get a little bit difficult to actually compute these things by hand. And so the way inverse dynamics usually works that you derive the equations by hand, right? So you basically kind of do what we just did with free body diagrams, equations of motion, okay? Okay. So you want to derive these equations or derive these expressions for the net joint forces by hand, okay? Then you're going to input these equations into some kind of code usually. So usually using MATLAB. MATLAB is usually a good software for handling data. Okay. Right. So you derive those equations, you input them into MATLAB. So MATLAB's going to do most of the calculations for you. Okay. At the same time, you're going to load in the kinematics data into MATLAB as well. So that's probably going to be some very large data table that you load into MATLAB. Okay. Okay. And so you input the equations that you derive by hand, you load in the data into MATLAB, and then MATLAB is able to compute all of your net forces and moments at the joints, as a function of time, and you'll be able to get kind of a nice, really nice data table from that as well. Okay. Another option for this is some kind of spreadsheet program as well. So like Google Sheets, Microsoft Excel, that it can do this as well. Okay. And so the real work, the real kind of task with inverse dynamics is to actually just derive the equations. Okay. So that's kind of why I spent so long in the previous example, showing kind of every single step in this process, because there's a lot involved. So you have to really be careful about the moment equation. You want to make sure you sum it around the center of mass. There's a lot that's involved in computing the linear accelerations as well. Okay, because that's the main work, right? And so for your exam, right? So how am I going to test you on this on the exam? So obviously, you're not going to have MATLAB available to you. You're not going to have Excel available to you. And so on the exam, what I'm going to give you is basically a problem just like this previous example, where I give you all the dimensions. We assume all the kinematic data is known, and I want you to derive the expressions for the joint forces and joint moments at each joint. Right? And so I believe that's what the homework asked you to do as well. So the homework, basically, I give you this this collection of body segments, and I ask you to derive the equations for the net joint forces and net weight. Basically, just exactly as we did. Okay. All right. If you're curious about the MATLAB implementation, I do have a code, that's a sample code that's online that kind of shows this. And so that's definitely available for you to look at. That might be helpful for you for your project if you guys are doing an inverse dynamics analysis for your project. In fact, looking at the projects that are available or that a lot of your groups have chosen, I think that, this is very appropriate for that. So definitely would be good to take a look at that code for that. But for the midterm exam, this, you just have to know how to derive the equations here. Okay. All right. Any questions on this? Okay. All right. So unfortunately, I do have to cut this section short just because we do have to start muscle optimization next week. I do want to let you know that there is one more example in the notes. And so if you look at the end of the inverse dynamics notes, there is another example for how to do inverse dynamics of a bicep curl. Okay. A question in the chat. Let me see. Question, would it be necessary to plug in the kinematic data on the exam or no? So on the exam, I'm not going to give you any kinematic data. I think that's just kind of, that's just a time waster. And so for the exam, I'm just going to have you derive the equations and then that's it. Yeah. Hmm? Yeah, so if you do, I wish I had time to do this example too, but I would definitely check it out, just because these, just these problems just end up taking a lot of time. So definitely check out the bicep curl example in the notes. Okay. That's another good one to know. If anything, just to kind of give yourself more practice with, deriving these equations. Okay. The last thing I wanted to note before we end up today is, I want to make a little bit of a comment in terms of where do we start, this analysis. Oh, another question in the chat. Let me see. Okay, so is it okay for homework we use MATLAB to multiply the matrices? Yeah, that's totally fine. In fact, that's kind of what I expect as well. So yeah, don't multiply the matrices by hand. Either do it with your calculator or with MATLAB. Okay. Okay. So what do I mean about where to start? So I'm going to scroll back way back up here. So let's look at the previous example. Let's look at it from the beginning. Okay. Right. So this was the example that we just kind of worked through, right? So we had, basically 3 body segments, 3 joints. And if you recall, right, we started this analysis from the bottoms. We started at the foot. Okay. But, that kind of begs the question of, why did we start here and why did we not start up here, right? Or even if you wanted to be, truly, chaotic, you could start it from the middle too as well if you really want to. But generally speaking, you want to start your analysis from one of the exterior body parts. Okay. Okay. So the reason we started with the foot here, if you recall, is that, at the foot, I didn't draw it here just because I kind of forgot about it when we were starting today. But at the foot, we had information about the external force that's being applied on the foot, right? And so if you look back at your notes from last Wednesday, you'll see that, we had information about the normal force, Fg, being applied from the ground to the foot, okay? In other words, at the foot, we had information about the external force that's being applied there, okay? Okay. So generally, when you're deciding where to start an inverse dynamics analysis, you usually want to start with the body segment where an external force is being applied. Okay. The reason for this is that, if you do this, you'll be able to solve all three of your equations of motion explicitly, right? Okay. And so what I mean by that is that, you're going to get Fx, Fy, and M for that joint. And because you have that input of the external force, you'll be able to get explicit expressions for Fx, Fy, and M. Okay. Now, can you start from the other end and work your way back? Yes, because technically speaking, the equations are not going to change. But if you don't want to be extremely patient, and if you want to kind of solve your system kind of sequentially, usually it's best to start wherever the external force is being applied. That way you can kind of, once you kind of finish with that segment, you'll have kind of explicit expressions for Fx, Fy, and M at that joint. And so when you go to your next body segment, these now become the inputs that you can plug into that equation, and then you can solve for Fx, Fy, and M at the next joint, okay? So it's a little bit more of a convenience thing, and so you can definitely, start from way further in, or you start with the middle segment, and eventually you're going to get expressions for everything. But it's just makes a little bit more sense if you start from the outside where an external force is being applied, and then work your way in. Okay. All right. Any final questions on this? Okay. All right. So that's all we got time for today. So definitely, especially as you're studying for the exam, definitely take a look at the bicep curl example, just because that one has some good stuff. It's a lot of the same of what we just covered with the squat, but just getting another look is always useful, especially when you're studying for the exam, right? And so when we come back on Monday, we're going to start a new topic, and so we're going to start with muscle optimization. So we'll talk about what that means and how that kind of fits into our dynamic analysis. And then we have our midterm exam next Wednesday. So thank you guys for coming this week. I know it was kind of a shortened week because we had the day off on Monday, but I appreciate you guys all being here. I hope you guys have a good weekend, and I will see you guys next week.
Professor. Professor. Sorry.
Yep.
Do you happen to do office hours over Zoom or just in person?
I have it both over Zoom and in person.
Okay, then I'll probably Zoom you in a bit when you get back to your office.
Yeah, the Zoom links are on the Canvas site. So if you go to the Canvas site on the homepage, there's Zoom links for the office hours there.
All right, perfect.
No, the topics are kind of getting.
Hi.
Said to come to you if we
Okay. Okay. Yeah. So I have another group of two actually too. Yeah. So let us send me an email.
Yeah.
Just do, and then I'll introduce you over email with the other. Okay, so this works out perfect.
That was great. All right.
Yeah.
Thank you so much. Yeah. Do you know what topics are still available?
They've already chosen topics, so they want to do biomechanics of force.
Okay. Oh, yeah. That's cool.
But I'm sure they're open if you want to discuss with them or something else you want to do.
We're just having to have a group.
Okay.
We don't go in person. What are we gonna do?
Yeah, just send me an email and then I'll help you guys.
Okay. Thanks.
Yeah.
Appreciate it. All right. Yeah. Okay.
Yeah. All right.
Yeah.